In problem 1.7, we wish to prove a statement known as the Ehrenfest theorem, which basically states that the change in the expectation value of momentum is equal to the expectation value of the negative of the partial of the potential energy as a function of x. And we want to show that this asserts that expectation values obey the classical laws. So let's sort of split this into two parts. In the first part, we will sort of derive this theorem. We will show that this expression is true, and then in the second part, we will sort of explain how this shows that expectation values obey classical laws. So let's start by proving it. So what we want here is that we want to take the time derivative of the expectation value of momentum. Now, in this section, we've sort of already found how to actually, what the expectation value of momentum actually is. We know that the expectation value of momentum, which is denoted as bracket P, is equal to negative I times h bar times the integral of psi star, which is the complex conjugate of psi, times the partial of psi with respect to x dx. So if we want to take the derivative of this with respect to time, that's just a matter of using product rule on this inner term, because psi star and psi both depend on both position and time. So we do d of expectation value of p with respect to time is equal to, and we have our same constants at the front, negative I h bar, and then our integral, and using sort of product rule on this inner term, we get partial psi star with respect to time times partial psi with respect to x plus psi star times partial of psi twice with respect to x and with respect to t, and this whole thing under dx. So one of the things that we sort of want to show is that we want the Ehrenfest theorem, which states that this d of expectation value of p with respect to t is equal to a potential term. And so far, the only expression that we actually know about, which includes the potential energy, is the Schrödinger equation. So let's sort of just write that down as a reference right now. So let's write down that the Schrödinger equation states that I times h bar times the partial of psi with respect to time is equal to the negative of h bar over 2m times the second partial of psi with respect to x squared, and then added with the potential v times the psi itself. Now we can also do the exact same thing with sort of the complex conjugate version of this, and we say that negative IH, let's do this in a different color actually, we can also say that the corresponding component, or the counterpart to this, is negative IH bar times partial of psi star with respect to time is equal to negative h bar over 2m times the second partial of psi star with respect to x squared plus v psi, where we sort of add this extra negative sign at the front here because we're taking the complex conjugate of all these terms, and under complex conjugates the imaginary terms get a negative added in front of them, and immediately what we sort of see is that our sort of expressions can be subbed into our integral. So first off, we have a negative IH partial psi star with respect to time here, and also we also have a second order partial with respect to psi of x and t, and one of the things we know is that psi is in c squared. Let's do this in black. So what does it mean when we say psi is in c squared? What that means is that psi itself and all of its derivatives are continuous and finite. And that makes sense. We require that sort of to have a physically realizable wave function, and as a result of psi being in C2, what we say is that we can say that as a result, the partials of psi are commutative. And what this means is that we can make the following claim. We can say that sort of the partial of x of the partial of psi with respect to time is in fact identical to the partial with respect to time of the partial of psi with respect to x. So hopefully you already know this from calculus, but if you don't, I would encourage you to sort of review this idea. But any function that is in C2 sort of has this property. Its derivatives are effectively commutable, and psi necessarily has to follow this, because if it didn't, then it would have sort of like these infinite derivatives, and that would result in sort of non-integrable wave functions that don't really make sense physically. So because of that, we sort of require this. What we can say is that this green part right here, which we're going to sort of, this green part, which I'm going to sort of box in as a point of interest, can be simplified, and this sort of becomes the partial with respect to x of the partial of psi with respect to time. And from there, we can simply just plug that into sort of this Schrodinger equation that we have, because we have the negative IH bar term at the front, and we plug everything in, and this should give us sort of 4 terms in our integral. So now that we sort of have defined our Schrodinger equation in terms of this IH bar partial psi with respect to time and also its respective conjugate, we can sort of plug this into our equation, the red and the green respectively, and this sort of ends up being how our equation simplifies out. And where here I've simply just distributed out the negative IH bar into each of these terms. So now we can sort of expand this, and we're going to get 4 terms. So this is a quite the intensive derivation that we're about to start doing. So let's just sort of go slowly. So this is going to equal, and we're going to start with the red term, because this one's the simpler one. Negative IH bar partial psi star with respect to time goes directly into this. So we're just going to copy and paste this over onto the bottom. And I'm going to add a parenthesis symbol, attach our partial of psi, whoops, that is a very painful, partial psi with respect to x. And I'm going to do the same thing here, where we sort of have our IH bar partial psi with respect to time, so subtracted by, and then this whole thing and we're going to add sort of another set of parentheses here, and then multiplied by psi star. And actually, we're going to move this whole thing to the left a little bit, because we left out our sort of partial derivative here. So we're going to do that. Add the partial with respect to x up here. And now we can sort of start distributing. So let's sort of do that right away. So this is going to equal the integral once again. And these sort of just go about how you expect them to go. There's no sort of operator that's getting distributed over, so it's just simply a matter of just applying or distributing our partial psi with respect to x in front of each of these 2 terms. So let's sort of do this whole thing in red, just to like separate out everything. So this is going to be negative h hat all divided by 2m times the second partial of psi star with respect to x squared times the partial of psi with respect to x. And we're going to distribute out the second one, so this is going to be plus the potential v times psi times the partial of psi with respect to x And that is sort of our left two terms. The right ones, let's distribute these out in green. So this is going to be two negatives make a positive, so plus h bar over 2m. And then the partial with respect to x just goes directly onto our second partial of psi with respect to x squared. So this is going to become a third partial. So partial 3 psi with respect to x cubed. And then sort of do the same thing here. So the negative carries over. So we're going to do subtracted by, and we're actually going to have to do product rule with this because we don't know whether or not the potential varies with position or not. So we're going to have to do subtracted by partial with respect to x of v times psi subtracted by v partial of psi with respect to x. And then this whole thing is going to be multiplied by psi star. So let's sort of, and of course, I just forgot, we have to also apply our dx terms at the ends of our integrals. So let's do that as well. And now let's just sort of write this down one more time, simplify it even more, or expand it even more, I guess, because we're not really simplifying this one at all. Definitely kind of a painful one. So let's just do this. I'm going to erase my integral actually here because I'm just going to copy paste it directly from the top. This is going to be, the front remains mostly the same, and then we're going to add on the sort of distribution that we've carried out. So plus h bar over 2m times partial cubed psi with respect to x cubed multiplied by psi conjugate, psi star, subtracted by partial v with respect to x of psi star. Finally, subtracted by v partial of psi with respect to x times psi star. Okay, and once again, we bring down our dx term to end our integral. So, what can we cancel here? Well, the first thing that we can cancel is that we recognize that these two are the same term. V psi, partial psi, actually, forgive me, I just realized there is a bit of a typo here. This should be psi star, in fact. There's supposed to be a psi star here, supposed to be a psi star here, and there's supposed to be a psi star here. Yeah. So these two terms are actually the exact same, so they simply cancel out. V psi star partial psi with respect to x, negative v partial psi with respect to x psi star, they are commutative, so therefore we can instantly sort of cancel them out, exactly like that. Next, we have negative partial v with respect to x psi star. This is actually what we want. And then we have these two terms, which evidently have to cancel out somehow. So let's sort of write this out in a little bit of a neater way. So this is equal to the integral, and let's sort of, because we recognize that this is h hat over 2m in front of both of these. So h bar over 2m, and we're just going to switch the order a little bit here. And we're going to say, we're going to start with the green one first. So partial cubed at the front, and then subtracted by h hat over 2m of all of this stuff at the back. And we're just going to erase this and move this over here. And with that, we have sort of our first term dx, and then our second term is going to be a subtraction subtracted by the integral of, and we're going to sort of rearrange this because of commutative property to make it look more like an actual operator. So we're going to make this look like psi star partial v with respect to x times psi, where all I've done is I've just sort of moved my terms around a little bit because I'm allowed to do that since everything's commutative here. And one thing we could even do is we can actually move the negative inside as well, in which case this would become a positive, and I would get a negative here and sort of enclose off this term here. I just realized I accidentally brought the star term in by accident. So let's just rewrite that for here. Okay, so evidently this is just equivalent to the expectation value of negative partial v with respect to x. This is just the formula for that. We always, for any sort of quantity, when we want to calculate the expectation, we sandwich it in between psi star and psi, as we talked about when going over operators. So evidently what that implies is that this is supposed to somehow cancel out to 0. So let us sort of try to figure that out, or puzzle out how this is supposed to be true. So we sort of already have the answer that we were looking for earlier in the form of this expression to the right, which is the expectation value of the negative of partial v with respect to x, and this is exactly sort of what our problem wants us to find. So that implies that this first integral term here has to equal 0 somehow. And because of that, we can instantly sort of, to try to prove this, we can sort of instantly get rid of the constants in front, because these will just like multiply out to the other side and equal 0 anyway. So what we're truly trying to prove is that we're trying to show that the integral of, and we're going to do this once again, sort of in green and red, and I'm going to move these around a little bit so that we can follow convention, so that sort of like the conjugate term goes first, followed by the non-conjugate term. So we're going to write this as psi star multiplied by the third partial of psi with respect to x cubed. And we're going to subtract this by the second partial, second partial of psi star with respect to x squared times the partial of psi with respect to x. And somehow, in some way, this is supposed to cancel out to 0. Now, hopefully, just from looking at this, you can recognize that one of the things that we can sort of do to try to get these two terms equal to each other is actually to use integration by parts, because psi star in green is 2 derivatives higher than the psi star in red term, whereas the psi term in green is 2 derivatives higher than the psi in red. So because of that, we can actually use u sub here, and doing it twice will actually make these two terms sort of equal to each other with an extra term inside of it. So let's sort of just try and start doing that and see where that ends, where that gets us and ending up. So let's just start right away. So we're going to use u sub actually on this green term. So I'm going to say we're going to set u equal to, and let's actually do some different colors here. Let's do blue and purple. Let's set u equal to psi star. So what this implies is that du must equal partial psi star with respect to x dx. And then let's do dv. So dv we're going to set as equal to partial cubed psi with respect to x cubed dx, and we're going to set v then equal to the second, so partial squared psi with respect to x squared. And we're basically doing this for the first term, so all of this sort of goes into here. So in that case, what this becomes is sort of using uv equals integral of v du, or uv minus integral v du, we get that this is psi star times in fact, it might be easier if we just copy pasted this text this way, psi star times this, and then evaluated from negative infinity to infinity, uv minus integral of v du, so subtracted by the integral of v du, so subtracted by the integral of, and we're actually going to sort of use the same convention that we did before of putting the conjugate first. So this is du. V goes sort of right after that. And then we're going to include our dx term right at the end here. So instantly, we can see that this first term sort of cancels out to 0 because we require that psi and psi star both go to 0 at infinity and negative infinity. Otherwise, our expression would no longer sort of be square integrable and would probably integrate to infinity. So because of that, this automatically goes to 0. We can cancel that out immediately. So what we have now is, let's write this out fully. So now what we have is that, sort of separate it like this. So we have that the negative integral of this subtracted by the integral over here has to equal 0. And we're a little bit closer. We've sort of, we originally started with psi star and a third derivative of psi. Now we have kind of moved one derivative over onto psi star and taken one away from psi. So we are one step closer to sort of getting it. So now we just have to do it again. And apparently this suggests that we will get sort of the same expression, and hopefully they will cancel out. So let's do this whole process all over again. So we're going to say that u equals the partial of psi star with respect to x. So that means du must therefore equal the second partial of psi starred with respect to x squared. And now let's do dv. So dv is apparently equal to the second partial of psi with respect to x times dx. So v is evidently equal to the partial of psi. Sorry, there's supposed to be an x squared here. Psi, partial of psi with respect to x. And once again, we sort of do this integration by parts term, and this goes down to what? U times v. So let's sort of get these terms out of the way here. So first off, this expression multiplied by v evaluated at positive and negative infinity minus the integral of v du, so minus the integral of, and we're going to do the same thing here. I actually forgot to apply a dx here. My apologies. That is my mistake. And we're going to do the same thing, same convention, sort of apply the star terms first. Let's just erase this extra thing here. V du, so we're going to get this term over here to the right times dx. And remember that we sort of have a negative at the front here originally, so this becomes negative and positive respectively. And instantly, hopefully what you see is that, well, we have this minus term here. And these two are the exact same terms, so evidently they cancel out to 0. So sort of now we're stuck with this last final term. So now we require, the only thing we need to sort of finish our proof is that we need to show that this expression must equal 0. And hopefully you see that if psi and its conjugate goes to 0 at positive and negative infinity, so too sort of must its derivatives. Because if we have some sort of wave function, it can do whatever crazy stuff here sort of at like near 0, but like as it gets farther away, it must necessarily even out to 0. So as a result of that, its derivatives all must go to 0 as well, because this sort of gradually approaches sort of a flat line. So because of that, any derivative of psi actually goes to 0 at positive and negative infinity. The same thing is sort of true for like the left side as well. Necessarily, if we don't want this to like integrate to infinity and we want it to be normalizable, we sort of require this. So because of that, any derivative of psi actually in fact also goes to 0, not just psi itself, and that also applies to its complex conjugate. Now, in a classical sense, what this is sort of saying is that we don't care what happens to our particle at infinitely far away. And that is reasonable. In classical physics, when we're dealing with sort of like gases or particles and stuff, we typically assume that our system is sort of closed off in some finite boundary and that it doesn't actually have any interactions or meaningful interactions at infinity. And sort of this is sort of the same thing, where we're assuming that our particle is sort of localized in a given area and that we don't really care about what happens to it at positive or negative infinity. So we are allowed to assume that. So because of that, both partial psi with respect to x and partial psi star with respect to x, both of these derivatives sort of have to necessarily go to 0 at positive and negative infinity. So as a result of that, this does indeed check out. And as a result of that, we do indeed have our Ehrenfest theorem. Because earlier on, we sort of had this expression, and this first term, sort of, we evaluated it out to this entire mess down here, and we showed that this does indeed equal 0, and we know that the term on the right here simply equals the expectation of negative partial v with respect to x, and this whole thing is in fact equal to, as we sort of proved up here, d expectation value p with respect to time. So this whole thing ultimately equals this. So therefore, we have that d expectation value of p with respect to time is in fact equal to the expectation value of the negative of partial v with respect to x. And therefore, we have solved sort of the first part of this problem. The final part of this problem is basically sort of, it's not really part of the problem, but it states that Ehrenfest theorem asserts that expectation values obey the classical laws. And this is something that I sort of want to make clear for a little bit. So let's kind of switch over to classical mechanics for a little bit. And in classical mechanics, we sort of have Newton's second law, which tells us that force is equivalent to mass times acceleration. However, we can also express this using different various other parameters, because we can express Newton's second law using momentum, and we can say that force is in fact equal to the change in momentum with respect to time. And if you sort of want to prove this, that's very easy to do, because we know that momentum is equal to mass times velocity. So the change in momentum with respect to time, well, that if we added a d over dt in front, that would just give us mass times acceleration. So because of that, force does in fact equal the change in momentum with respect to time. The second alternate form of Newton's second law uses energy. So the second alternate version states that force equals the change in the potential energy with respect to position. At least in one dimension, this is true. In higher dimensions, we would use gradients, but for now, let's just stick to one dimension. So I will not actually derive this. This one, the derivation for this one is a little bit more complicated, and we don't really have time to do that, but this is true. And if you want to sort of prove that for yourself, I highly encourage you to go look up this idea, this concept of expressing force in terms of the change in potential energy for a system. But this is necessarily true. So if we set these two equal to each other, what we get is that dp over dt is equal to, sorry, there's supposed to be a negative in front here, is equal to negative dv over dx. And this sort of is very similar to the Ehrenfest theorem, which states that d expectation value of p over dt is equal to the expectation value of negative partial v with respect to x. So the only thing that we're sort of missing here is the expectation value signs, right here and right here respectively. So sort of what this tells us is that if we look at a quantum system in terms of expectation values instead of wave functions, those expectation values do in fact obey classical laws such as Newton's laws of motion and energy and various other terms like that. So because of that, there actually is a way for us to sort of analyze a quantum system from a classical standpoint, and that is proven via Ehrenfest's theorem.